I'm Tim Ventura, and we're joined today by Srinjoy Ganguly, a quantum AI research scientist at Fractal, IBM Qiskit advocate and quantum educator, and clinical professor of practice for quantum computing at Woxsen University. Srinjoy has a bachelor's degree in electrical, electronics, and communications engineering, and an MS in artificial intelligence from the University of Southampton, as well as a second MS in quantum computing technologies from the Polytechnic University of Madrid. So, Srinjoy, welcome, and thank you so much for joining me today. Let me start by asking, what first got you interested in quantum computing, and what inspired you to pursue your current career path in education and as a quantum AI scientist?
Yeah, that's great. Actually, yeah, that's a great question. So I actually started with quantum. I mean, I just started exploring quantum computing while I was doing my internship in undergraduate back in 2016. So I was doing work on software-defined radios and signal processing aspects, and then from in a defense research team. And there my scientist, like supervisor, my internship supervisor, mentioned about quantum, and he said that you can explore maybe quantum communication. At that point I was not very interested because I was already doing signal processing, but I said that sure, I will go through. So that was my first encounter with quantum computing, and how quantum mechanical principles combined with the computing technology, and so on. And there I explored a bit of quantum teleportation. After that, I kept working on 5G wireless signal processing systems. So I went to Indian Institute of Technology, Kanpur, between 2016 to 2017, about 5 times, and carried out some research-based courses and projects on 5G wireless system development. And from there, slowly transitioned into AI machine learning, because even in signal processing we started using machine learning for estimation detection of signals. So then I started working on some AI machine learning projects, especially focusing on computer vision. But I was never able to get away from quantum. I kept on exploring quantum, and then I took several more courses from MIT in 2018 and kept exploring that. And during that time, I even got admit from Southampton University to pursue my master's in AI. But I never left quantum, and I knew that quantum and AI could be combined together in the future, because I saw some potential that these both are deep tech technologies, and sooner or later people will start realizing that we have to combine AI and quantum somehow to make some greater breakthrough. So that's how I transitioned into quantum completely, and then joined Fractal this year in January 2022, as a AI research scientist researching on variational quantum algorithms, quantum chemistry, and quantum finance.
Okay. Well, and again, you have such an incredible background and depth of knowledge in this, and that's why I'm so excited to have you on today to help educate people about what is going on with quantum computing as well as AI. Now, you did a recent interview in Analytics in India magazine, and there you discussed today's quantum computers being in
Yeah,
around the 100 qubit range. And
yeah,
you'd mentioned at the time that we need to see systems with thousands of qubits as well as quantum error correction in place before we could
yeah.
really begin to use them effectively. Can you tell me a little bit more about where this is, where it currently is and where it is going, especially in terms of quantum error correction? Because I understand that that is still a challenge in many systems.
Yeah. So quantum error correction is not my primary field of study, although I have explored it time to time, and even quantum error mitigation as well when we were doing our research at Fractal. So basically, where we are going with this is that we have two aspects. One is the physical qubits, and another is logical qubits. So for physical qubits, like the systems which the current quantum computing industries are launching are the physical qubits, and lot of these physical qubits actually make these logical qubit. And logical qubit is that qubit which will actually not suffer from any kind of noise. That means it's a perfect qubit, what we defined as like a fault tolerant qubit. So currently we are in the noisy era of quantum, which is we call the NISQ era, noisy intermediate scale quantum. And that's why I said in my Analytics India magazine that we are in the hundreds of qubits range, because indeed we are in that intermediate scale range and we have not surpassed thousands of qubits. And what we have seen is that with the quantum error correction mechanisms applied to physical qubits, then we can create one logical qubit with thousand, about approximately thousand physical qubits. And that's why people have this like, there is a lot of research basically going on to create more physical qubits, like all the systems which were launched of physical qubits. And from that we apply quantum error correction and algorithms, try to do more research to make better error correction strategies in order to get one or two logical qubits through which we can, like, develop some sort of preliminary applications on quantum.
Ah, okay. Well, now in terms of background on where things are currently at, so IBM just demonstrated a 433 qubit Osprey system. They have
Yeah.
plans next year for the 1121 qubit Condor system as a successor
Yeah.
to it. Now, I've again, what I've read is that quantum computers may actually require 50,000 to 1,000,000 qubits in order to solve many of the problems that scientists are looking at giving to them. How long do you think it may be before we see quantum computers begin to reach this point? Do you have any estimates I mean, maybe 5 years, maybe 10?
So yeah, I mean, in my previous interview as well with Analytics India, I mean, I discussed this issue. So currently, given the stage which we are, and this is linked to your previous question, since we are in the noisy era, noisy intermediate scale, therefore we apart, like, I mean, what I estimate is that approximately about a decade, like about 10 years, we should be able to have some lots of qubits, like about a million
Mm.
million physical qubits, which will be able to have hundreds of logical qubits. And then with those logical qubits we will be hopefully able to build some kind of scalable quantum applications with even like developer operations or DevOps in place as well. But I would like to add one thing here. So since we are making a lot of physical qubits, but side by side a lot of research is also happening on how to make a quality qubit. So also researchers are trying to build a qubit which has a longer coherence time, that means which does not get affected with the noise. If we are able to build a perfect error corrected qubits without having a need to make so many physical qubits, then our job is literally done, because then we have one logical qubit which is already error corrected, fault tolerant, it's free from any noise, and now we can use that to develop further applications and further research as well.
Ah, okay, okay.
Yeah.
So again, that's kind of the fundamentals. Now, the industry itself is literally surging forward on this, and that's one of the things that's so exciting for me on it.
Yeah.
Now, in addition to your university degrees and specialization in this area, you are also an IBM quantum educator and Qiskit
Yeah.
advocate, and
Yeah.
those are certifications as well. So,
Yeah.
can you tell me what those certs mean? And what are some of the duties or responsibilities that go along with that?
So currently, by giving a podcast with you, I am fulfilling one of my responsibilities as a IBM Qiskit advocate.
Okay,
So
there you go.
Qiskit, yeah, so that's one of the responsibilities. So as a Qiskit advocate, that means it's not only about IBM's library or Qiskit, it's more broader. It's basically quantum advocate. So so what responsibilities we have is that we promote quantum computing, we promote the education and research and development of quantum computing, we contribute to the quantum community, and move away any hype surrounding the research and surrounding the area of quantum, which many people have a lot of hype. So we are those people who remove these hypes, and we have realistic expectation and create realistic expectations among other community members in quantum, and give them a realistic view of how the technology, at what stage we are, how is it going to mature in the next few years, and why they should invest in this technology, why they should study this, and so on. So that's the job of a quantum educator combined with quantum advocate, Qiskit advocate.
Yeah. Well, so based on the experience that you've had so far, again, you're helping to dispel myths. You're helping to educate people about where things are at,
Yeah,
where things are going.
yeah.
What seems to cause the most confusion for people currently in terms of quantum computing?
So since I am also adjunct faculty at Woxsen University, so when I teach students and whenever I take training sessions, so one of the common doubts which I have is about the aspect of qubit itself, like what is a quantum bit, and like how these quantum mechanical properties like superposition, entanglement are actually coming into the picture to make this qubit. So this is the one of the most common doubts which I face when I train students, because and I mean that's natural. The reason, because we are all habitual to doing classical computing. We know that classical computers work with bits which are either 0 or 1. So our brain does not process that, like how can it be in between, which we define through quantum superposition. So therefore, when I first time defined this concept that yeah, qubits are in superposition, they are on and off at the same time. So people say that, okay, how is that possible? But that's nature. That is possible. That's what happening with the laws of quantum mechanics.
Well, if I could build off that, and this is kind of, I think this may be an area of confusion for me. Now, a
Mm.
moment ago, you talked about physical qubits, which we could
Yeah,
represent as like the spin state, right, of an
yeah,
atom. I think. You also talked about logical qubits. Now, would a logical qubit, the way that I would interpret that is that would be a collection of several physical qubits to
yeah,
correct for potential errors in any one of them, right?
yeah. Absolutely, absolutely
Okay.
correct. Yeah, yeah. So many physical qubits actually, they error correct and create one logical qubit, and it is free from any kind of noise, because nowadays qubits are subjected to a lot of environment noise, which we call as a decoherence of qubits. So they are not able to sustain their quantum mechanical properties for a longer duration. Those three properties, superposition, interference, and entanglement, should be sustained for a longer duration of time in order to make some kind of useful quantum application or run a very large quantum circuit on a computer. But if you are not able to sustain that, then we would not be able to make a very relevant or significant application, because we are facing noises. So therefore our probabilities of getting a accurate result decreases a lot.
Oh,
So
okay.
yeah,
Well, so that's something that I think a lot of people don't. Again, I didn't know this myself until recently. The qubit solutions decay, so you can't leave it like with transistors. You could just leave it on and it stays on, or off and it stays off.
yeah,
It with the case of the qubits, though, those values decay into random noise
yeah,
quite
yeah,
rapidly. So
quite rapidly.
yeah, so if I understand correctly, you basically have to make your calculation and then move that to some other kind of system to store the values, or else you're stuck. It will decay within, I believe, well under a second, if I remember right.
Yeah, yeah, absolutely. You are correct. So there is qubit decoherence times and coherence time, which we measure in quantum hardware. And each quantum hardware company defines their coherence and decoherence times. And from that, we get to know that for how larger circuit or for how longer calculations or computations can be done on that particular quantum hardware. And
Ah,
people are
okay.
trying to come up with new benchmarks as well as we speak about.
Well, so there are currently three. I mean, there are many more than three, but I think three of the big companies that are involved with this. You've got IBM, Amazon, and Google. They're all involved with this. I mean, Google was one of the forerunners. They did a lot of the early, truly groundbreaking work. IBM as well. They're currently doing just a lot of amazing groundbreaking work. Um, for professionals like yourself, because they've all got their own kind of different approach to it from a company perspective, do you see a lot of similarities between how these different organizations approach quantum computing? And are they working towards standards so that professionals like yourself can use your skills across any of their systems? Or do they really have kind of siloed systems where you have to, for instance, you may have to specialize in
Mhm.
IBM, but then
Yeah.
Google, you would have to retrain for it.
Yeah, so I mean, like they do have similarities. I mean, even as a quantum professional, because I mean they work on the same kind of technology that is superconducting qubits. Amazon currently does not have their own quantum computer, but they are in the process to build it, and they are also taking the approach of superconducting qubits, which IBM and Google has done.
Okay.
And yeah, so Amazon, basically, even our organization like Fractal also has tie up with the AWS, Amazon Web Systems, for like the bracket access. So Amazon provides their interface. So bracket acts as an interface between, like, our code and various other quantum hardware. So AWS just provides those quantum hardware on the cloud, and we can run our code on those cloud with the help of the bracket. So bracket acts as an interface. So that's, like, for AWS. And as for IBM, like, mostly we use IBM because they are also publicly available systems, and they have also introduced the pay as you go model. So that brings a flexibility in research, which was not earlier present. But like, what I could say, I'm not very familiar about Google setting up like a particular benchmark to measure, like, the quantum performance. But I can say about IBM that IBM has come up with two nice benchmarking system. One is the quantum volume, and another is the circuit layer operations per second, which
Hmm.
is known as clops. So IBM has really set a benchmark, I would say, in, like, how the quantum performance should be measured for a quantum computer, and everyone has actually started to use that. Even Google and Amazon, and even every other hardware company have started to define quantum volume, clops operation of their hardware, and so on.
Oh, okay. Well, and again, I think the reason that this is important for people is, and again, as this industry starts to move forward, you have the hardware, you have the science, that you have things that are being physically developed, right? And
Yeah, yeah,
as you mentioned, that they started with single qubits, and then we had strings of qubits. Now we're going to logical qubits, which require even more physical qubits to make it work. So the actual technology is moving forward. Now, on the business side of things, that is an area where it sounds like industry is getting involved, and they're saying, hey, we don't want to wait for the technology to be there. We want to be able to use it when it's there. So, like, one thing I wanted to ask about was, you're certified in Qiskit, but I've also heard references to programming in the Python, Ocean, Q Sharp, and
yeah,
the Circ languages. So, if from that perspective, again, you'd mentioned that you're able to use pay as you go. They're web-based simulators, if I understand
yeah,
correctly. You can actually
yeah,
run online with IBM, for instance, and it sounds like
yeah,
Amazon as well. Um,
absolutely, yeah,
and
absolutely.
and then you can actually write code in these languages as well and run it on these machines in the cloud, right?
Yeah, yeah, that's absolutely correct. So, like, you have heard that correctly, and most of the programming is done in Python language, because that's very easy to learn even for beginners, and provides a lot of flexibility as well. So, I mean, for Ocean, I mean, I have not explored Ocean that much, because Ocean is for D waves quantum computers, and D waves
Mm.
quantum computers are specialized annealing based quantum processors. So I have not used them as much, but we have used at Fractal, at our company, and even before, also before Fractal also, I have used Qiskit and Circ. Circ is from Google, and Qiskit is from IBM. So these two are popular, and they have a lot of similarities in between as well. And about Q Sharp, I have not used it, but that's a wonderful language from Microsoft. The reason, because Q Sharp can be used with C Sharp language, or Visual Basic. And so on, and even with Python also, you can even run Python as well. Well, if you use Q Sharp, so it has integrations. But why I personally like Qiskit is because Qiskit also provides a lot of integrations with all of these languages which you mentioned. So Qiskit can be integrated with Ocean to run, like, jobs on annealing processors. Qiskit can be integrated with Circ, It can be integrated with another library like PennyLane, which is for quantum machine learning research specifically. So I mean, yeah, so Qiskit has a lot of integrations, and it also has the largest community as well. So if you face any issues, you can, like, just go and ask the community, and they are always wonderful people to help you out there.
Oh, wonderful. Well, and again, I think it's important for people to know that the business side of things, the programming, the computer science side of things, that's already moving forward, and that it will meet the hardware when the hardware is there. Now, in terms of
Absolutely.
hardware, and again, let me apologize. I just lost my question there. IBM is they're moving towards circuit-based computers. One of the things that interested me when I saw the 433 qubit system, I think all of us remember that the photo of Google, right, where they had the wires hanging down,
Yeah.
and yeah, it looked like something out of the Matrix.
Yeah.
IBM's looks like a chip. It's packaged like a chip. Now, I understand that it still requires cryogenic cooling, right? So it still
Yeah.
requires um, some specialized setup, I guess, compared to a standard computer. But nonetheless, it's a packaged
Yeah.
semiconductor. Um, do you see easy integration of technology like that into data centers in the future? Or do you think it will always require kind of a big standalone box somewhere?
So that's a very nice question actually, and what I feel is, I mean, you can integrate those systems at a certain point in time. But before integrating them, one of the major aspect which needs to be addressed is the presence of a quantum memory device. Because if we start speaking about data centers, then they have, I mean, operating systems and storage devices running all in parallel. But for as for quantum, we do not have a proper memory device. Recently there was some breakthrough, I'm not able to recall right now, but a team of researchers have created a quantum memory device which can, I think, if I'm not wrong, it can last for about 3 to 4 seconds or something. That's a huge milestone in itself, because before
Yeah.
that we have not been able to achieve 3 to 4 second milestone. So that means up to 3 to 4 seconds we are able to hold the quantum mechanical properties. That means we will be able to encode our classical data into a quantum chip, which can act as a quantum memory, and it will remain there. It's something like, we have, like, for classical we have like RAM. So for random access memory, like, we transfer, or like we have a hard drive, we transfer all the data. Even if we, like, access the hard drive after 1 or 2 years, the data is there, it's not lost.
Yeah.
So it's like, recorded in those bits patterns. So a similar kind of breakthrough will be required in quantum, what I feel, from my perspective. Then we can integrate very easily with data centers, and that should not be an issue. The reason, because in classical computing we have a lot of maturity already existing in the technology, so it should be far more easier integration once we reach that stage.
Okay. Okay. So again, it's just a matter of time as things move
It's
forward.
just a matter of time. Yeah.
Now, so one of the things, and again, this goes to your unique specialization. Uh, Obviously, you have a master's degree that's in quantum. You also have a master's degree in AI. How do you see these two fields working together in the future?
Yeah, so that's the field which you are mentioning is quantum machine learning, or like, yeah, a subset of quantum AI, or maybe, yeah, broadly you can call them as quantum AI. So that's one of the aspects even we are also focusing at Fractal, and even before Fractal I have focused on from application viewpoint. So and the existence, or the development of variational quantum algorithms have enabled the integration of AI and quantum. The reason, because variational quantum algorithms, the work they do is very similar how machine learning models work. We can have parameterized quantum circuits which can have several parameters, and they can be trained just like a machine learning model. So that's how, like, it forms like a hybrid system of classical quantum mechanism, where, like, we have our model in the form of quantum circuits, parameterized circuits or variational circuits. They have trainable parameters. We train them for a specific purpose, then we take the measurements out. It goes to a classical computer for optimization as well as loss calculation, and then again fed back to the quantum computer. So that has like so variational quantum algorithms are one of the primary things how quantum has been combined with AI.
Okay. Okay. Yeah. Also, natural language processing. This is another specialization of yours. This falls into artificial intelligence, if I understand correctly, right? This is part of the branch of AI as a science. But
Yeah,
um, you specifically noted when I was doing the interview notes, you specifically noted this was a focus area for you. So I thought I would follow up on that.
yeah,
How can quantum computing and NLP work together? And I should mention for people, when I think of NLP, I'm thinking of Siri, right? Or Chat GPT. Now, Siri is voice based, Chat GPT is keyboard based, but they're both working with natural language processing. So a person types into it the way they would talk normally to another person, and it
yeah.
responds. How can quantum computing assist in those areas?
That's an excellent question actually, and the question which you're asking about is about quantum natural language processing, which is QNLP, where I have worked on. And so QNLP is a beautiful idea. First of all, I would say the reason because I mean, there are several uh, like you know categories from which QNLP can be done, but the aspect which I have focused on is mathematically derived. So for that, what we do is that we can represent sentences or any meaning of a sentence with the help of diagrams, and that comes from diagrammatic quantum theory. And from those diagrams we can convert them into circuits, and then we can run them on a quantum computer. So the branch of quantum NLP itself is at a very emerging stage. Like it's very like very early, I would say. It would still take about I think 7 to 8 years to have that kind of maturity which you are talking about, like Siri or something. But even in classical NLP we can see like chat GPT and Siri, we can see that there has been a lot of development happening. So QNLP not only focuses about the reasoning which can do with quantum computers, it focuses on better reasoning abilities about the language. That means better performance, better accuracy, but also it focuses on a broader aspect which is called the quantum compositional intelligence, as defined by Bob Cooke, who is the pioneer of QNLP. So he defines this quantum compositional intelligence, which comes directly from the aspects of QNLP, because language is something which is strongly tied to the cognition in human beings. So that's how we understand each other when we communicate. So that defines also our level of intelligence. If a person knows multiple languages, then they are considered to be intelligent because they can translate between those languages in their brain. They don't need a translator if they know 3 to 4 languages. So it is inherently rooted with the cognition system in our brain, and that's why. And quantum composition intelligence, the broader aspect of QNLP, goes towards AGI. That means artificial general intelligence. That means in future we should be able to, and this is just my opinion. Everyone can, yeah, of course, everyone's opinion is welcome. But what I feel is that the field of QNLP will go to QCI, quantum composition intelligence, and from that we will be able to have at least a little bit, a small version of artificial general intelligence, which people are researching about, going from
Okay.
AI to AGI.
Yeah, yeah. Well, and so let me highlight that for people. And I've done stories on this in the past. So AGI systems today tend to be somewhat fragile, right? And I
Yeah,
think Chat GPT, which isn't even really attempting to do that, but that's kind of an example of it. When you take them outside of what they're good at, or you ask questions that are maybe not as flexible as they could be, these systems just really fall apart. And so
yeah,
they're very good facsimiles of intelligence, but they lack the
yeah,
depth and robustness. It sounds like
exactly.
what you're talking about is being able to use quantum calculations and maybe
Yeah.
the uncertainty, I guess, that goes with qubits that have both values, and maybe apply that to creating more robust, rich, and human-like AGI in the future.
Absolutely. I would like to, yeah, this is a absolutely like lovely point which you have added. And I would like to add just one more point to this is like, I mean, you can already see like how with classical NLP we have been able to like, have these kinds of wonderful systems like Chat GPT. So now you can imagine if we can do so much with qubits, and not only qubits, but even quantum hardware companies are working on qubits. That means multi-dimensional quantum level systems. So if we can have, let's say, like qubit is a 2 level quantum system, what if we can have 3 level, what if we can have 4 level, or up to n levels? Then you can imagine the possibilities, like how much feature and information extraction and connectivity can be done with the help of these multidimensional quantum systems. So that's where even QNLP, and not only QNLP, but even quantum AI in general could shine, because we are getting this large space to have a lot of information encoded in a very small package. Maybe quantum memory will have just a little bit small package, and maybe it is cooled cryogenically, but we have a lot of information stored because it has so much levels, and they all can be connected, and they can decipher, or we can infer information better from them, better than our classical computers.
Wonderful. Well, Srinjoy, thank you again so much for your time today. And thank you for helping us understand. This is technically very complex. I think it's going to take all of us a lot of time to start to wrap our heads
Yeah.
around where this can go. But, the potential for it is so remarkable. So
Yeah.
thank you again for your time today. Let me
Thank you so
close
much.
by asking, what comes next in your own career? And what's the most exciting research in the quantum computing industry that we should be keeping an eye on in the headlines?
That's a great question. So personally, for me, I will be going for a PhD in quantum hardware. And as for the research directions, I would take a look. Like, I mean, I would be keen, and I think, I mean, everyone is very keen to look at the progress which is happening in current quantum hardware, because in the coming few years a lot of interesting developments are going to happen in quantum hardware, from which, like, quantum software and maybe quantum operating systems will be also developed for these quantum computers. So yeah, that's one of the research area which everyone can take a look at: quantum hardware development.
Wonderful, wonderful. Joy, thank you again so much for your time today, sir.
Thank you so much. Thank you so much.